Welcome to the final video of our transformer series. In this video, we are going to discuss about the decoder architecture from scratch. In the first portion of this video, we are going to look at the encoding-decoding strategy in deep learning, and we will see how this differs in transformers. Then in the second portion of this video, we will uncover different layers inside the decoder and we will look at its role and functioning. Now this video is jam-packed with lots of valuable information, so stick till the end. And if you're coming to this channel for the first time, then I recommend you to go through all the videos in transformers. Those videos will give you immense clarity on every single component of transformers. But if you already have a little bit idea of transformers and you only want to understand the decoder architecture, then you can carry on with this video. And if you find this video valuable, be sure to hit the like button and subscribe to this channel to never miss an update. And without further ado, let's get started. Let's start by understanding what is this encoder-decoder architecture in deep learning. To illustrate this, I will take a classic example of machine translation, where we will be translating English sentence into Spanish. For instance, if the English sentence is I like pizza, then its Spanish translation will be me gusta la pizza. Imagine that we are using an RNN-based model. In this step, the input words will be processed sequentially one after another in the encoder. As each word is processed, the hidden state of the RNN accumulates the information, and eventually this will have the entire summarized context available. Once the encoding process is completed, we feed this summarized context to the decoding block. Decoder takes this as an input along with the start token and produces the first output prediction. At each step, decoder takes this previously generated word along with the hidden state and generates next prediction. This process continues till it produces the end token. This start token indicates decoder to start its decoding process. And similarly, this end token indicates decoder to stop the decoding process. This is the core mechanism of RNN-based encoder-decoder model. And that's how the training also works for RNN-based models. Each step is sequential and takes a long time. But let's see how does this change in transformer-based models. In transformer-based model, we still follow the encoder-decoder strategy, but with a crucial difference. Instead of processing words sequentially in the encoder, we process everything parallelly. The entire input sentence is fed into the encoder at once, allowing for significantly faster processing. The output of the encoder is then passed to the decoder block. If you have forgotten, the encoder takes word embeddings as the input. If the input has 3 words, then the encoder will produce 3 new contextual representation for each of these words. These contextual representations are produced by processing the input word embedding through multiple layers of encoder block. Now the output of the encoder will be fed into the decoder along with the start token. And decoder will start its decoding process and generates the first prediction. Let's say this prediction is the Spanish word me. Now in the next step, the decoder will take in the predicted word me as the input along with the start token as well as the encoder's output, and it will make its second prediction. Let's say this is the Spanish word gusta. Then in the third step, it will take this gusta as the input along with both the previous words as well as the encoder's output and make another prediction. This process continues till the decoder produces the end token, which will indicate it to stop the decoding process. This is how encoding-decoding works in transformers during inference time. Now, what is this inference time? See, a deep learning model has 2 stages. One is the training stage and second is the testing stage. In this testing stage, we use the trained model to make real world prediction on an unseen data. This testing phase is known as inference. I'll be using this word often throughout the video. So whenever I use inference, consider that we are talking about the test phase and not the training phase. So coming back, this is how encoding-decoding looks like in transformers. But wait, I know something will upset you. This process of decoding is sequential. It's not parallel. We put a lot of brains to make all the operations of transformers parallel because we wanted faster training. But we could only achieve it in the encoder part and not in the decoder part. I would say yes, the decoder must work sequentially at inference time. We don't have a choice. Because each predicted word influences the next predictions. We can't predict all words at once. We need to see what has been generated so far to make further predictions. And that is why we take the predicted word as the input to the next step in the decoding. So decoding has to be done sequentially during the inference time. It cannot be done parallelly. But this raises an important question. Does this also mean that training also have to be sequential, or can training be parallelized? If we want to train LLMs, we want faster training. This sequential processing during the training time will limit us. So let's see what happens during the training of the transformers. Let's try to reproduce the training process step by step. The encoder processes the entire input sequence and produces its output all at once in a single forward pass. The decoder takes in the encoder's output along with the start token and makes the first prediction. Let's say the first prediction is the word la, and it's a wrong prediction, but it's fine. Our model is not trained yet and it can predict incorrectly. What we will do here is we will calculate the loss between the predicted word and the actual prediction. The actual prediction should have been the word me. So we'll compute the loss between these two words and we will use this loss to adjust the model's weight parameters through backpropagation. But let's not worry about the backpropagation for now. And let's continue our decoding process. In the next step, instead of feeding the decoder with its incorrectly predicted output, we feed the correct word from the target sequence. Remember, we are teaching the model to make accurate predictions, so we don't want to pass the incorrect word predictions, but rather the correct target word. So rather than passing the word la, we will pass the correct word, that is me, and let the decoder predict the next word. Let's say in the next step, it predicted the word odio, which in English translates to hate. And this is also an incorrect prediction, but it's fine. The model is still learning. We will again compute the loss between these two words and use it for backpropagation. And in the third step, I'll pass the actual word from the target label gusta instead of the predicted word odio. And this process will continue till the decoder produces the end token. Now notice something interesting. We are not relying on the decoder's previously produced output. Instead, we are always providing it with the correct target label. So this process doesn't have to be sequential because we know the entire target sequence already. This is coming from the dataset. We are completely discarding the predicted word except using it for the loss. But we can still make this entire process parallel and calculate the loss between all of the words in one go. So this is a key difference in transformers and it's very important. The transformers behave differently during training and inference. The training can be done parallelly for encoder and decoder, but inference cannot be done parallelly. Inference has to be sequential while training is done parallelly. Alright, I hope it's clear. Now let's move forward and see how do we parallelize the training of transformers. A brute force approach could be to create multiple instances of the decoder and process different words parallelly. Since we already know the target sequence, we can create these combinations and feed them in the different instance of decoder. The output will be predicted parallelly by all of these different instances of decoder. Then we can compute the loss and can perform the backpropagation. At first glance, this might seem like a good approach because we are speeding up the training process and performing everything parallelly. But there is a problem. While we are processing all the words in parallel, we are also running the decoder multiple times. So if my sentence has 4 words, then we need 4 instances of the decoder. If my sentence has 1000 words, then we need 1000 instances of decoder. And all of the calculations in these decoder blocks will be repeated but for different words. This means that my computational cost scales linearly with the sequence length. I will be using 1000 times more computation than I would be using if I had processed everything in a single forward pass. Just like how we were doing in encoder. See, in encoder, we were taking the entire input sentence and processing it in a single forward pass. So is it not possible to pass the entire target sequence to the decoder at once and process it in a single forward pass? And I would say it is possible, but there will be a problem if you do that. See, the decoder block has self-attention layers just like we had it in encoder. Self-attention, as we know, creates contextual representation by attending to all the words in the sequence. If we pass the entire target sequence at once, the decoder's self-attention mechanism will create the new context vectors by seeing all the words. Which means for the prediction of my first word, I know all the words that come after it. But that was not the case in inference time, was it? Because in inference, I only pass the previously predicted words in the input. I don't know the future words. To make the prediction for my second word, I only pass the previously predicted word, that is me. To make the prediction for my third word, I only pass the previously predicted words, that is me and Gusta. I am not passing the future words because I don't have access to those future words during inference. But if you pass all the words at the same time during training, to process this word, I will also have the access to all of these words. And that should not be allowed. This is cheating. The model will get used to seeing the future words during training. And if that happens, it will struggle during the inference when those future words won't be available. This is the classic case of data leakage. Data leakage is when the model has access to information during the training that it won't have at the testing time. If that happens, the model's prediction during the real world inference time is going to be poor. So in short, we are stuck in a dilemma. If we train the model sequentially, it will take more time. If we create multiple instances of decoder, then we will take more computation. And if we go by parallelizing the decoding step by passing the entire sequence at once, it will create a data leakage issue. So it feels like that every option comes with a major drawback. It's like we are caught up between devil and the deep sea. Which one to choose? Is there a way to get best of both the worlds? Can we make training parallel while ensuring the model does not cheat by looking at the future words? Is it possible? And my answer is thankfully yes. And we will find our answer in the first layer of decoder, that is masked multi-headed attention. The authors of the paper have found a simple yet effective way to deal with this strategy. Before we go there, let me make something clear. What we want is to parallelize the decoding during training by passing the entire target sequence at once without causing data leakage. And this can be done with the help of masked multi-headed attention. So let's have a look. What is this masked multi-headed attention? To understand masked attention, let's take a quick recap of self-attention. In self-attention, we start with the word embeddings. For decoder, our input is Spanish words. Let's say we have 5 Spanish words: start, me, gusta, la, and pizza. For each of these Spanish words, we will have a corresponding word embedding. Each word embedding is of size 512. So the overall input matrix is of size 5, 512. Now we will multiply this input with 3 weight matrices WK, WQ and WV, each of size 512, 64. This multiplication of input embedding with a weight matrix is known as linear transformation. This linear transformation step is going to produce us with key, query and value matrices, each of size 512, 64. Because the input is of size 5, 512 and is multiplied with the weight matrix of size 512, 64. So the result is 5, 64. Alright, now our self-attention operation starts. First, we multiply the query with the K transpose. This multiplication of query and keys is going to provide us with the similarity scores. The Q is of size 5, 64 and the K transpose is of size 64, 5. So the result is going to be of size 5, 5. These values indicate the similarity score between the input tokens. For example, this V23 score indicates the similarity between the Spanish word me with the Spanish word gusta. This V35 indicates the similarity between the Spanish word gusta and the Spanish word pizza. These similarity scores also capture the relevant dependencies from the sentence. In the sentence "Mi gusta la pizza," there can be a high dependency between the word "mi" and "gusta," indicating that the subject "mi" is performing the action "gusta," that is to like. So the similarity score between the "mi" and "gusta" is going to be higher. Similarly, there can be a high dependency between the word "gusta" and "pizza," indicating that the pizza is the one that is being liked. So there can be a high similarity score between the word "gusta" and "pizza." Now these similarity scores undergo a scale and softmax operation, where we scale these individual scores by dividing it with the value 8. Now why this value 8? I have covered this in a separate dedicated video. You can check that out by clicking on the upper I button. But for now, understand that these values are divided by a scalar constant, and then we apply softmax over them horizontally. So the sum of these scores is going to be equal to 1. Softmax operation converts a set of values into probabilities. So if you do the sum of these values, then it's going to be equal to 1. Okay. Then we multiply this resultant matrix with the values matrix to obtain the final output of the self-attention. The overall equation looks something like this, with the scalar division of root of dk over here. Now these are the contextual embeddings obtained for the Spanish words. So the first embedding will be the new embedding of start, second will be the new embedding of the word me, and so on. So this is entire self-attention operation. Now we want to see what is masked attention. For masked attention, let's expand this equation for each individual Spanish word and see how it looks like. You will find that the new contextual vector is obtained by a combination sum of the value vectors, and the proportion of these value vectors is determined by the similarity score here. Now for masked attention, we don't want the tokens to see the future tokens, which means that to obtain the new contextual embedding of the word start, I don't want any contribution from the future words, which means that their similarity score and the value vectors must not contribute in the new contextual embedding. Similarly, to generate the new contextual embedding of the word me, the future words gusta, la, pizza should not contribute, and so on. And the sum of the remaining similarity scores should also be equal to 1. In short, it should look like that the new contextual embeddings is obtained by looking at only the previous and the current word, not the future word. So how do we obtain this? The answer might be much simpler than you think. What if we apply a mask that can diagonally remove these values? In short, what if we nullify these values or make them 0? Can we do that? Yes. What if we apply a mask that can look something like this? What I've done here is that I have assigned all the diagonal values to negative of infinity and the rest of the values to 0. If you add these two matrices, then the result will have these values turn to negative infinity, because the sum of any value with negative infinity is equal to negative infinity. So all the red marked values is going to be turned to negative of infinity, while the rest of the values is going to stay the same because it's going to be added with 0. And with this kind of resultant matrix, if you apply a scaled and softmax, the softmax is going to turn the negative infinity to 0. So all of these values is going to be turned to 0, while the rest of the values are going to be converted into probabilities. And this way we have achieved our purpose. If you multiply this matrix with a value vector, then all of these future tokens will be nullified and their contribution will be eliminated from the self-attention operation. And that is why this variation of self-attention is known as masked attention. With masked attention, we have solved the problem of data leakage, and now we can pass the entire target sequence all at once and can process them in a single forward pass. Okay, so the training of transformers will look something like this. In a single forward pass, the encoder will process all of the input English words, and it will generate the new contextual vectors for each of the English input word. Now this generated contextual vectors is going to be fed into the decoder, and the decoder is also going to take the entire target sequence and process it in a single forward pass. For each of the input word of the decoder, it is going to make a prediction. So if the number of input to the decoder is equal to 5, then the decoder will produce 5 output predictions. Now these output predictions is going to be compared with the actual target label, which is me, gusta, la, and pizza. So we will compute the loss between the predicted word and the actual labels. Based on this loss, the weights of the decoder and the encoder is going to be updated in the backward propagation step. So to summarize, a single forward pass of encoder, then a single forward pass of decoder, computing the loss, then backward propagation, update the weights of decoder, then backward propagation, update the weights of encoder. This is how the training of transformers is going to be done. But please note, the inference is still going to be sequential because the inference depends on the previously predicted word. During inference, we need to pass the previously predicted words for the next step of decoding. And this is a crucial difference in transformers. Transformers behave differently in training and inference. So please keep this difference in mind. Alright, so I hope everything is clear for you. I know what might be unclear for you is that what goes inside this decoder step. What are the different layers? So let's look at each individual layer of decoder one by one. We already looked at the first layer of decoder, and that is masked attention. Note that this is a masked multi-headed attention, which means that there will be multiple heads of masked attention processing the input. Each of this head is going to capture a different interpretation from the sentence. And overall, all of these interpretations is going to be combined to generate a richer contextual embedding. And these contextual embeddings will be generated by looking at only the previous words and not the future words. And that is why this is a powerful layer of decoder. But if you notice it carefully, then you will realize that this layer has limitations. And the limitations is it is an attention layer. Attention layer processes each word parallelly at the same time, which means that there is no word order between the words. And the word order is important in NLP. So before we feed the data to masked attention, we apply a positional encoding over the input. I have created a dedicated video on positional encoding explaining how the positional encodings allow the attention layer to interpret the word order. If you have not watched that video, then you can check it out by clicking on the upper I button. But for now, remember that we will generate the positional encodings. These positional encodings will be of dimension 512, which is the same as the dimension of our decoder input. And then we will perform an element-wise addition between positional encodings and the decoder word embeddings. And this combined result is going to be fed as the input to masked multi-headed attention. Okay, so we have covered two crucial layers of decoder. Let's move forward. In my previous video of encoder, I was stressing the fact that we apply add and norm layer after every major layer of encoder and decoder. So after masked attention, we are going to apply an add and norm layer. This add and norm layer performs two key operations. One is it adds the input of masked attention to its output. Notice the arrow connecting the masked attention's input to its output. So let's say the input of the masked multi-headed attention is Z0 and its output is Z0 dash. Both of these is going to be of same dimensions 512. So we can easily perform an element-wise addition between them. So this add part is basically the element-wise addition of input to mask multi-headed attention to its output. These kinds of skip connections or these kinds of additions are known as residual connections. These residual connections help us to stabilize the training of the model. After this addition, we have a layer normalization step. This layer normalization prevents the notorious issues of vanishing and exploding gradients. Both of these steps are crucial to stabilize the training of the model. I've covered this add and norm layer in depth in my encoder video. So if you have not checked that out, please click on the upper I button. Alright, so we have positional encodings, masked attention, add and norm layer. What comes next? Next we have something very interesting. So far, we haven't used the output of the decoder. So it's time to bring it into the picture. Think, what is the decoder's job? It is to generate output predictions, right? But what does this output prediction depend on? It depends on two key factors. One is the words generated so far, and second is the information captured by encoder. Now, we already took care of the first part. We have a masked attention layer which attends to the previously generated tokens. Now we want an attention layer that can attend to the encoder's output. And that's where we have cross attention. Cross attention is going to take two inputs. One input is the output from this layer, and the other input is coming from the encoder's output. See, self-attention helps a word understand how it is related to other words in the sentence. Cross-attention helps a word understand how it is related to encoder's output. Instead of attending to itself, we will be attending to the encoder's output. Remember, I told you that encoder produces a contextual word representation for every single word as it had in the input. These contextual vectors are also 512 dimensions. So is our output coming from this layer. So we can easily perform a cross attention between them. Let me show you in detail how cross attention looks like. The key difference here is that instead of generating key, query and value from the same embedding vectors, we are going to generate key and value from the encoder's output. So let's just assume that this vector corresponds to the word I, this corresponds to like, and this corresponds to pizza. We will be generating the key and value matrices from the encoder's output, and we will be generating the query matrix from the decoder's input. So this can be the contextual vector obtained after the add and norm layer for the token start. This can be the contextual vector obtained after add and norm layer of the decoder for the word me, and similarly we will have contextual vector of gusta, la and pizza. Now this is the only difference. Rest is the same. The equation of self-attention, we multiply the query and the KT transpose. The query is coming from decoder while the key is coming from encoder. So our similarity score will be calculated between these two. Then we perform softmax horizontally and convert these scores into probabilities. And then we multiply it with value vectors to obtain the new contextual vectors. Now these produced contextual vector has now context from both decoder's words as well as encoder. The overall equation is the same. If we expand the equations for all the words, then it will look something like this. We will obtain new contextual vectors for each word in the decoder. And these contextual vectors are obtained by a different proportion of value vectors obtained from the encoder's output. These proportions are decided by the similarity score. This is a way to dynamically adjust the word's context as per the relevance. Note, in the RNN based encoder-decoder strategy, we used to have a single summarized context of the sentence. This summarized context was then passed to decoder block, and each word in the decoder was forced to use the summarized context. But that is not the case here in transformers. Transformers dynamically adjust their context based on the relevant part of the encoder, which means that if there is a high similarity between the word gusta and like, then the new contextual embedding of gusta will be obtained by a major portion of likes encoder output, while a lesser portion of pizza and eyes encoder output. So instead of using a summarized version of the sentence, we use this dynamically adjusted context as per the relevance. This will result in even accurate predictions. Each word in Spanish will know its relevance to the words in English. And based on these relevance, a better translation can be produced. There is also another major benefit of this. Remember, in RNN based model, we used to sequentially encode the input sentence. If the input sentence is very long, then this summary context, or which is a hidden state, will almost forget about the words at the initial part of the sentence. And that was a major issue for us. But this will not happen with transformers. the encoder will generate a contextual vector for each of the word that it had received in the input. So if the input sentence in English had 100 words, I will have 100 new contextual vectors for each of that word. And I will be using these contextual vector to perform cross attention between the words in Spanish. Now, some relevant word in English, even if they are in the beginning of the sentence, they can still relate to relevant word in Spanish, even though if they are at the later end of the sentence. So no matter how long my sentence is, we can still attend to all of the words and extract relevant information. Isn't this fascinating? How simple yet powerful each component of transformer is, and how beautifully it is crafted. But let me blow your mind with another interesting fact about cross attention. Cross attention is a fundamental and an important block of multimodal learning. What is multimodal learning? It is when a single model can learn from two different types of input. One input can be text and other input can be image or audio. Have you noticed that in ChatGPT you can upload image as well as you can provide some input text, and ChatGPT will be able to understand both the text and your sentence both at the same time and can generate a single response for you. That is multimodal learning, where you are providing two different kinds of input to the model. The model is able to seamlessly understand the information from both the kinds of data. In cross attention, one part can be your text, while other part can be your image data or audio data. Or you can even have audio on one side and image on the other side. Cross attention will be able to obtain knowledge from the other type of data and will be able to integrate it in a single matrix. It will learn the relationship between the words and the image, and combining both of this knowledge, it will generate the new context. This is like giving transformers a human-like ability. You know, we humans, we capture input from different senses like eyes, ears, and nose, and can combine these stimuli to form a single understanding. Similarly, transformers can also integrate multiple types of data. In the near future, robots will be able to seamlessly process inputs from different modalities, learning to connect them and develop a unified perception. They will be able to mimic us humans in a better way. So I hope you are starting to understand how each component of transformers are fitting together. So let's move forward in our discussion and study about the remaining layer of decoder. After cross attention, we have another add and norm layer to stabilize the training. This is followed by a feed forward network and another add and norm layer. This feed forward network takes in 512 dimensions input, expand it to a higher dimensions input like 2048, and then reduce it again back to 512 dimensions. This expansion to higher dimension is done to capture richer and complex features from the input which lower dimensions could not capture. It also adds more number of parameters to the model, allowing the model to learn complex data. And then the reason why we reduce it back to 512 dimensions is because we want to keep the size consistent to 512 dimensions no matter which layer we are at. This feed forward network also adds some non-linearity. The operations in cross attention and mass attention had linear transformations in them, and no non-linear function has been used there. So we need to introduce some non-linearity in the model. This non-linearity is introduced with the help of feed forward network. I have talked about feed forward network and its importance in depth in my encoder video. I highly recommend you checking it out to solidify your understanding. But this is how one block of decoder looks like. We stack in multiple decoder blocks on top of each other. In the original attention is all you need paper, we have 6 encoder blocks stacked on top of each other. What happens is, whatever is the output produced by the first decoder block is passed as is without processing it to the next decoder block. And this goes on for 6 times. Note, the positional encoding is only applied once before the first decoder block. And we have something interesting at the end of the 6th decoder block. After all blocks of decoder, we have a final prediction layer. So far the decoders have produced the 512 dimensional contextual vectors for each word. These vectors are needed to be converted into predictions. Our objective is to convert a 512 dimensional output produced by the decoder to a Spanish word, which is going to be our prediction. So how can we do it? Let us assume that we have 100,000 words in our Spanish vocabulary. These 100,000 words can have start token, end token, words like me, gusta, la, odio, pizza, and so forth. So this vocabulary will have 100,000 Spanish words. Our prediction is going to be one of this word. We can easily achieve this by performing a linear transformation on this 512 dimensional output. We will perform a linear transformation of this embedding with a weight matrix of size 512, 100,000. So the result of this linear transformation is going to be a 100,000 dimensional vector. Now this vector can have values in any range. What we want to do is we want to convert these values into probabilities so that it can be converted into prediction. So we will add some bias and apply softmax over it. And in turn, we will get a 100,000 dimensional vector where the values are converted into probabilities. So the sum of these 100,000 values is going to be equal to 1. Now each of this value correspond to a particular word in Spanish. We can assume that the first dimension correspond to start, second dimension correspond to end, and there will be some dimension that will correspond to word me, some dimension that will correspond to word gusta, and so on. Our prediction is going to be the word which has the highest probability. If I explain in detail, then we will have 100,000 values. Out of this 100,000 values, there will be a particular value whose value will be highest among all of these 100,000 values. We will choose that value as our output prediction. If that value corresponds to the word me, then me is going to be our output prediction. And this is how we convert 512 dimensional output from decoder to a particular word prediction. If the decoder had 5 input words, then the decoder is going to produce 5 output predictions as well. So the number of outputs produced by the decoder is always equal to the number of input words provided to it. During the training, we will compute the loss between the output prediction and the actual target label and use it for backpropagation. And this covers our entire decoder architecture. But before you close this video, I will ask you to hold on, otherwise you will miss out on an important detail. As I told you, the number of outputs produced by decoder is always equal to the number of inputs it receives. So does this logic also applies during the inference time? As the inference is sequential, let's look at what happens during inference time. In the first step of decoding, it will receive a start token, which will ask decoder to start its decoding job. This will produce a first output prediction, let's say me. In the second step of decoding, we will pass this me word along with the start token. So now the input to decoder is 2 words, which means that the decoder will also make 2 output predictions. But we were not expecting this, were we? We were expecting that during inference, each sequential step produces a singular output prediction. So what do we do with the 2 outputs produced? We simply discard the first output prediction. We only keep the output prediction correspond to the word me. Let's say this second output prediction is the word gusta. So in the third step of decoding, we will pass this word gusta along with start and me. And the decoder will produce 3 output predictions. In this case, we simply discard the first 2 predictions and only keep the prediction corresponding to the word gusta. So this is what happens during inference. Also notice that masked attention is still applied during inference. We are not disabling it. If input to this masked attention is 3 Spanish words, then the masking will still be applied. This means that the first word will not have access to the next 2 words. The second word will not have access to the last word. So masking is still applied even during inference time. Now you might ask me, Jay, why do we still apply masking during inference? Didn't we keep the masking only for the training? And I would say we cannot change the architecture from training to inference, the architecture has to be same. This mask layer will have weight parameters. These weight parameters are trained during training. And if we disable these train parameters during inference time, then our predictions will be inaccurate. The model will be confused. So we have to keep the architecture same and we still have to apply masking. With this, we complete our transformers playlist. We have covered couple of crucial topics of decoder in a single video. I wanted to cover all of that in a single video of decoder and not break it into parts. Let me know if something is unclear for you so that I can make a dedicated video on it. I hope you are able to grasp the complete transformers design from scratch. It was immense pleasure for me to teach you this concept. If I could, I would give you a certificate of accomplishment for completing this playlist. It's not easy to understand transformers architecture, and if you have understood it, you have shown some immense intelligence. And I highly request, if you have found this valuable, then please do hit the like button and subscribe to this channel. You can also send me a super thanks or become a member of this channel. These gestures help me to continue bringing quality content for you. So thanks a lot for joining me in this journey. For now, signing off.